Yes, more malty stuff. You got it. So, I mean, this is kind of our master list. We can come back to this and look at it a little bit later. I'm going to start with some substitution and elimination. With alcohol. Okay, so boop. And let's pull one out here. Let's see. Trying to find a good one. Was there a specific one that tripped? Oh, someone's in the waiting room. Admit it. There we go.
I have an elimination one from the practice exam thingy that.
Okay,
Yeah.
yeah, I can do one of those as long, yeah. So which question was it?
I think it was 5, but let me double check.
Okay.
In the second part, he had like 2 rings and it looked like a dumbbell or whatever. Like,
Okay, yeah, I see it. All right, so we've got
I
this.
sent you.
You sent me one?
I sent you an updated list.
Oh, thank you. There we go. And then we're using concentrated H2SO4 and heat. And we are asked to determine the major organic product. So I guess for this one, it's kind of important to remember the mechanism. So we've got H2SO4, which looks like this. H. And then if we put in all of our electrons, Okay, so first thing that's going to happen, I'm actually going to redraw this. So our OH or alcohol is going to grab one of these hydrogens. So the electrons are going to move back on here. So now we've got a good leaving group, right? We have a good leaving group. So water is going to leave. Goodbye, see you later. And now we're going to have a positive charge on that carbon. But right now we have a secondary carbocation. And what we want to do is actually make that more stable. So we're going to have a hydride shift. I mean, obviously we have a lot of hydrogens going on, right? Like we've got a hydrogen over here, we have a hydrogen over here. But in order to form a more stable carbocation, which hydrogen do you think is going to move? The one on the left or the right?
The right, because it's a tertiary. It
Yep,
would make for tertiary.
exactly. So we're going to shift that over so that we can make a tertiary carbocation. And this question doesn't actually ask for the mechanism, so if you're able to just do all of this in your head, that's fine. But if you're not, you can kind of like work through it. Okay, so now we have a tertiary carbocation. And we have a deprotonated we have HSO4 basically floating around in our mixture, right, in our solution, right? So it's actually going to come in and be like, hey, I needed that hydrogen. I'm going to take it back. Actually, let's start on the other side. Yoink. So those electrons are going to move into a double bond, basically. Yeah, and then we end up with yeah, it kind of looks like a barbel.
Literally what I was thinking.
Yeah. So we end
I was
up
like, oh,
with 15, and this is the more substituted, right? Because we have a methyl here, right? So it ends up being the more substituted alkene. And then so does that make sense to everyone? How do you feel about that?
Yeah, it's really helpful.
Okay, cool. Now, I don't remember what the question was that I actually saw in the Discord, but I do know somebody was asking about this one, and this is in substitution and elimination reactions of alcohol. Question number 8. I figure we can do it.
yeah.
Yeah. So we have this. What was the actual question with this one?
Well, she was more wondering about the Walden inversion and the backside. Well, it's the same thing. So I think she was just slightly confused. She thought it was more about positioning and not what's going on in the problem. But I think I might have helped.
Okay.
But this is a good one.
Yeah, we can still do it anyway. Nope, that's too many. That's not even supposed to be there. Okay, so for this one, we're asked to give the reagent's conditions to perform the following reaction. Assign the reaction as addition, elimination, substitution, or arrangement. So, I mean, I guess the first thing we should probably notice is the substituent, like where it's changing. So this is the carbon where we have the change, which happens to be allylic. So we're probably going to have a nice SN2 reaction here. And so it would be substitution, because we're basically taking this whole thing here and we're replacing it with this whole thing right here. So we're substituting. And we're substituting with cyanide. So we would just use our Na plus, negative charge on our cyanide molecule. And I think that's all you would actually have to do with this question. And yeah, it would be backside attack because since SN2, they happen at the same time, right? So you have your leaving group is leaving and your other group is coming in. So the only way it could happen is a backside attack. So it would create that Walden inversion. Okay. Let's try mechanisms involving alcohols. I did do the pinnacle arrangement the other day. Let's do Sorry, deciding on one. If you have a number that you want me to actually do, just shout it out. Let's see.
For me, I'd say 17, but
You
yeah.
want to do 17?
I mean, if anyone else has one, go ahead though. Yeah.
Yeah, I'm gonna check the chat just to make sure. Okay, nobody's in the chat. All right, I'm just gonna do 17 then. Let's do number 17. All right, so this is 17 for mechanisms. We are starting with and there's a double bond here. Reacting it with HCl and methanol. And we end up with an aldehyde. Oh, double bond there. Okay. So, first thing we want to notice about this is that we have an acid with our methanol. This basically, it's going to protonate our methanol, so our methanol is going to have 2 hydrogens. And this is what we're actually going to be reacting with. So we have our oxygen, our methanol, and our 2 hydrogens. So we have a positive charge on here. And one of these alcohols are going to come and snag a hydrogen. The electrons are going to move back on the oxygen. That's because this is our Lewis acid, Bronsted acid, and this is our Lewis base, Bronsted base. So then if we redraw this, well, now we have water, which is a very good leaving group. So water is going to say, see ya. Got better things to do than hang out here. And we're going to have resonance in the next step. Because it's going to leave behind this positive charge. Which is going to do a bunch of different things, because either our alkene can move over, so we could draw it that way. And the positive charge moves over here. Or, now I wish I could go back the other way. Or our oxygen can form a double bond, right? So if we imagine that instead happening, we end up with something that looks like this. And this has a positive charge. So now our deprotonated methanol is going to come in again. And it's going to re-grab this hydrogen. These electrons are going to move back on that oxygen. And you end up with this. You will want to draw that hydrogen there because now you have an aldehyde. So yeah. Oh, and then we also should label. So we've got our Lewis acid, Bronsted acid, Lewis base, Bronsted base. We always have to label that. And I think that's it.
I have a quick question about this one.
Sure.
Why isn't it grabbing the hydrogen that's attached to the chlorine? Why is it going to the methanol?
This is the HCl is a very strong acid. So when you put these two things together, before you even mix it with this, right? Like these two things have already been added. They're already going to react with each other such that you end up with two hydrogens on your methanol.
So it's because of that methanol that we're taking it from that instead of the HCl?
Mm-hmm.
Okay.
Yeah.
Kristen, is it also because of the fact that it's not labeled like 1 and 2, so that's why we just assume it's all mixed together?
Mhm.
And that's also why?
Yes.
Because I had the same question. I was like, why is it not pulling from the HCl?
Yeah. So that's all one step. It's like they're both in the same solution. It's not like putting HCl first and then adding methanol. It's all together.
Okay, cool. Thanks.
Yeah. And the reason why we want to do that is because if we were to just put HCl in instead of like the methanol, nothing would get then like the chlorine is not going to come and then deprotonate again. It's a very strong acid, so it's just going to kind of like dissociate and protonate with the hydrogen. But then you're not gonna get like the next steps over here.
That makes sense. Thank you so much.
Yeah, you're welcome. Okay. And then next one. Multi-step synthesis. Okay. Does anyone else want to do another mechanism problem, or can I just move on to multi-step synthesis?
Girl, hit that multi-step.
All right, let's do it. Let me pick one. We have so many in this section.
Mm-hmm.
Does anyone have a favorite? Let's do I'll start with number 14, if no one has a suggestion. So we are given this to start with, and we're told that we are ending with this beautiful creation over here. Yeah, I think I got it. Okay. So first thing, I always compare what I'm starting with to what I'm ending with. So this has 1, 2, 3, 4, 5. We've got 5 carbons and an alkene. Pretty simple. Over here we have 1, 2, 3, 4, 5, 6, 7, 8. We've got 8 carbons, a ketone, and an alkyne. So 1, 2, 3, 4, 5. Well, let's start with how do we make a ketone?
With PCC?
Yep. You would need a secondary alcohol with PCC that would make us a ketone. And how do we make an alkyne?
You could do like the Br2 and then have excess NaNH2.
Yes, so we could do like a Br2 and then NaNH2. I guess that would be second step. And then we would have to follow up with protonating it. Yes. And then we are also adding 3 carbons. So we're adding 3 carbons. What is a good way to add 3 carbons?
It's adjacent, so it would have to be an epoxide, right?
Mm-hmm. Yes, that's a really good thing that you noted that too. Yeah, so when we look at our alkyne over here, we see that yeah, it would be like the next one over. It's not directly attached to the alkyne. So that would mean that it's an epoxide. However, we're adding 3, not 2. So we probably have a nice little like methyl kind of sticking out of here. And then the follow-up step would be H3O plus in order to protonate it and turn it into an alcohol. Okay, so we have a bunch of things here that we can do. Now we just have to like kind of like put the pieces together in the right order. So we are starting with 5 carbons and an alkene. What do you guys want to do first?
The alkyne stuff first, right?
Yeah, let's do the alkyne stuff first. So let's throw some bromine at it. And that's going to add bromine to either side here. And then we want to just take everything away. Basically the bromines, the hydrogen. So we're going to do that. The excess Na and H2 plus the H2O to reprotonate the end. So that's going to give us this looking thing. So it'll have the hydrogen on the end there. And let's just double count 1, 2, 3, 4, 5, just to make sure that we didn't forget a carbon anywhere, because when you have the alkynes, it's really easy to forget a carbon. Okay, so now we have an alkyne. So we did this. We kind of have to add the alcohol group before changing it into a ketone. So let's go ahead and do our epoxide. We have to do that Na and H2 first to get rid of that hydrogen. So let's do that. Now we can add our epoxide and reprotonate. So remember, it's going to attack this side. This is going to swing open. Oops. 1, 2, 3, and then there's our OH. Okay, so we did that. And then what's our last step?
PCC.
PCC. Yeah, so there we go.
I have a quick question.
Sure.
So I don't know if it was the practice test or the homework, but it had a similar question like this. And it had made it into a trans alkene, but it also was with PCC. The question was asked on Discord. I don't know if it was answered. Does it matter if we use the PCC first or the NA with the NH3 liquid ammonium? Does it matter what order we use those in?
I'm pretty sure that you can use them in either order. I don't think the liquid nitrogen, like the NH3 liquid, would affect the OH.
Okay.
Check that though. I don't know if that would just be like in your notes.
I know during office hours she had did it and she put I believe she put the liquid ammonium first and then the PCC, but I wasn't sure if there was a reason why she did it first or if I could have just did the PCC and then switched it into the alkene, if that makes sense.
I'm gonna see if it reacts with alcohol. Ooh, it might. I think it does actually react. So you should do you know what? I will ask Dr. T before I give you an answer because it's not, you haven't learned any of these reactions either. So I don't know.
Okay, well, in the meantime, I'll just do it the way it is in the homework and how she went in over office hours. I just didn't know if it mattered, but I'll just stay safe and do it the way she did it.
Yeah,
Thank you.
no problem. Number 22. Let me look at number 22 here.
Also, Kristen, really quickly, for this one, you could also use the Na2Cr2O7 one, right?
Yep, that's correct. The sodium
Okay.
dichromate. Yep.
Okay.
Because for the secondary alcohol, they both do the same thing.
Okay.
You know, I was trying to find the answers to those questions earlier, and I think I understand. So we have NaNH2, right? So NH2 is negative. It can deprotonate alcohol.
Yeah. Yeah,
So that's why
exactly.
you wouldn't do that before.
Wasn't it in the homework? Didn't she do it before the PCC though? I think PCC, let me see if I can find the question. I think she
Yeah,
did.
that's what, sorry. Yeah, I meant that's why you wouldn't do the PCC before. So doing the NaNH2 first is
Wait, isn't it NH3, not NH2? Sorry, not to.
Yeah, we were
That's
the question was about the liquid ammonium.
Yeah.
Ammonia. But I don't know. It doesn't actually seem to be covered in the notes specifically. So it is a really good question. I'm probably gonna send her an email just to clarify. I mean, it might be like a tidbit in one of the homeworks, like you know how they give you like little notes at the bottom. one of them might have the answer somewhere, but I don't see anything.
So it'd be
Go ahead.
question then. Wouldn't alcohol deprotonate the liquid ammonium and then become water?
Um, I don't know. uh,
That's the only thing that came to mind.
yeah.
So
I mean, when
maybe.
I look it up, it looks more like a substitution reaction where the nitrogen actually takes the place of, which, yeah, then it would have been like leaving group, and then the nitrogen would attack the positively charged carbocation. So possibly that might be what would happen. But I'm just going to check with her because that's not actually a reaction that you've learned. Like, we don't do a whole lot with nitrogen in that way.
yeah, and just to clarify, it's for the practice exam 2, number 2, question 14.
Okay, I'm gonna write that down. Question 14. Yeah. All right, so somebody requested number 22. So we're going to do that one now. And then we're ending with this. Okay. So we are starting with a 5-carbon ring with an alkene. So we have 1, 2, 3, 4, 5 carbons. We have an alkene in the ring specifically. Here we end with, so we still have our 5-carbon ring, but we've added 1, 2, two more carbons. So we've added 2 carbons. We have an alcohol. And we have a phenyl group. So let's figure out how we would actually make any of these things. That process. So I guess using some retrosynthesis, that's probably where I would start, right? Is that probably at some point we had something like this. That then added to the ring. This is kind of a weird one. And we are going to want to get rid of that alkene on the ring. So let's talk about different ways to get rid of an alkene. So what are some things that we could do to it?
Yes.
What's that?
Oh, I would say what you call it, to add an alcohol to it, but you can't add an alcohol. You can't add the substitution when an alcohol is there because it'll react with it or something like that, right? Or I don't know. So I mean, I guess if you were to add an alcohol, you could use what you call it, the HGOAC, H2O, NaBH4, or the anti what would you call it, Markovnikov version, the
Right.
BHTH.
That dish.
Yeah.
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 Those were the two that I was gonna say as well. That's the only thing that makes sense right now.
Yeah, so I would say that's probably a good place to start. Yeah, and it doesn't matter which one you use, just because it's equally substituted on either side. The thing is symmetrical, so it really doesn't matter like where
Okay.
you actually add it. But I will do the HGOAC2, H2O, NaBH4. And stick the alcohol right there. So now we have a secondary alcohol. And we know we're gonna have to add this. So honestly, what we're gonna need is for this carbon to have to somehow get a partially positive charge, right? Because once it's partially positive,
Oh.
you know, the positive and the negative, they attract and we can make a bond, right? So I mean, if we're thinking about doing this in the least possible amount of steps, what do you think we want to do to the alcohol?
Could you use PCC? That might be wrong though. I don't know.
No,
Oh,
it is actually correct. Yeah, so if we did PCC, that is going to, and this one is just, it just feels weird, but that will change this into a ketone, right? And because of resonance that's there, because electrons do move, right? So we end up with a partially positive charge here because it spends part of its state with a positive charge and the electrons just go on the oxygen. So we can really just like add this. This would be our reagent then for a step. So first it would need to be stabilized with a positive ion, a cation. We have that. 3 phenol. And then we would need to protonate it. I'm going to erase this just so there's some more space here. And that would turn this back into OH because it would get protonated by this. So now we have to change this into, oh yeah, I forgot to note, this is a transalkene, right? So that's important to note because we have two reagents that change an alkyne into an alkene, but it's either cis or trans. So what is the trans version?
the NaNH3 liquid.
Yeah. So we've got NaNH3 liquid. And that would be our last step. And it doesn't react with the alcohol, so that must not matter there anyway. Interesting. Okay. Any questions on this one?
I'm sorry. So why do you use NaNH3 instead of like, could you use like Lindlar's catalyst too, or no?
So
That was,
Lindner's catalyst changes it into
yeah.
the cis alkene.
Oh, okay,
Yeah.
because it's trans. Got it. Okay.
Yep.
There we go. Thank you.
You're
I was like,
welcome. Oh, you're good. Okay.
I think an easy way that had made it for me anyway for remembering that is I think 3 isn't even, so it can't be 2. So it's going to be the odd one. Whereas the 2 is, you know, the same.
Mm-hmm.
Kind of silly, but it works for me. Figured.
Yeah, I think that makes sense.
That problem was really weird, honestly.
This one?
Yeah,
Yeah,
I would have
it was
never.
really weird. I feel like we don't usually see this even like as a reagent.
Yeah,
So like having to use it as a reagent instead of as the reactant is just kind of, it just feels awkward.
yeah.
Yeah, I'm not a fan of this one.
So
And honestly, I
do you
just said the
think there's
PCC thing because you said the partial positive. So I just said like, well, I guess in a C double bond O, the C is the partial positive. I don't know. I just guessed though. So
Yeah.
do you think there's a likelihood we're actually going to see the sodium, is that acetylide?
Yeah, that's a sodium acetylide with the phenyl group hanging off the other end.
On the exam? Because I've seen that a handful of times throughout the homework. But it's,
I
yeah, it's not
I-
used very often, so that's why.
Yeah, I can't really guess what's actually going to be on your exam or not. I mean, also, I guess what throws is usually we see the acetylide and then, I mean, we paired a lot with like bromine. Bromine is a good leaving group, right? Where here, it was more, you know, just looking for the carbon with the positive charge. So this one was definitely a tricky one. I feel like she's not going to do this to you on your exam. I would hope not.
yeah, I
Cool.
noticed for the first one, it was way easier than the practice exam. So I mean, there's that, I guess.
Hmm.
Still don't want to, uh, underestimate it, and yeah.
Yeah. Oh, I'm gonna
Yeah.
check the chat. Sorry. Okay. Yeah. So hopefully not something this complicated, but it is good for your brain to try different things. What is another good one that we could do?
You do 23.
Sure. Let's do 23. It's another one like this. So we start off with an alcohol and we end with I mean, they write CH3 here. You don't really need to write that, but because that's really the same thing as that. So either way works. So we start with 5 carbons and a secondary alcohol, and we end with 5, 6, 7, 7 carbons. We still have an alcohol group, although it's sharing that carbon now with another structure. We've got this ketone. Yeah, so I mean, this is going to be similar to the other one because we have this OH group where we're going to be adding to this carbon. So the best way to do that is to make it such that that carbon has a partial positive charge. And then we can go ahead and add, I mean, to make
Aldehyde
this
or something? Oh.
aldehyde.
Yeah, well, or no, right? Oh, whatever.
Oh, let me,
Yeah.
well, the thing with I don't think we can just stick an aldehyde on there because there would be nothing. We need something to actually do the attacking, right? So if we have a positive charge and then
So PCC first, then I guess add an aldehyde, maybe? I don't know.
that's okay. No, it's okay.
Yeah.
So PCC is a good first step. Let's
Yeah.
do that.
Yeah.
So now we have this ketone. So this carbon has a partial positive charge. So now the question really is like, what should we add? And this is a really weird one because, you know, we look at this and we're thinking like, well, that's not an epoxide. Are we adding, so we know it's not an epoxide. So we're thinking like, is it like an aldehyde or something here? And it does kind of look like it's an aldehyde, but the problem is that these both have accepting carbons, right? So we can't really just like have a reaction when we just have these partially positive charged carbons. Like we need something to actually do the nucleophilic attack. And what is generally good at that? We've been using it a lot. We're adding 2 carbons.
Oh.
Yeah.
Yeah.
I know, this is another weird one. So what
Oh,
we're
and
Are
then
gonna
you like
do,
fully thinking that, but being like, no, that can't be right. No.
I know, it's so
Oh.
it's so awkward. So we're actually going to react this with our just a 2 carbon acetylide, so it's just, you know, that, and then protonating it. That's going to add the 2 carbons that we need. So let's redraw this. So that's going to reprotonate this, and we're going to end up with this thing at the end. Now we did learn a reagent
Yeah.
that turns an acetylide into here, a ketone, didn't we?
Yeah, the HgSO4, H2SO4, H2O one. Yeah. The only
Yes.
reason I remember that one is because it's a Markovnikov, Mercury
Yeah, here.
Markovnikov one. That's, yeah.
So it ends up with a ketone.
Yeah.
So that's actually what we're going to use. So to get from here to here, we use H2O, HgSO4, H2SO4. And it ends up with a ketone. So awkward, but it works. Those are definitely, they definitely get like harder as you go down the list, I feel like. So yeah. I guess we have time. Do you want to do one more of these multi-synthesis? I could go back to acetylide, cumulative alcohol problems.
Really quickly, Kristen, can you go for one of the acidity, what's called Bronze acidity problems again? Like how you did yesterday, really quickly.
Sure.
I know the practice exam had one of them. I think it was like it was a practice exam too. I know it was like somewhere around the beginning. I think it was problem number 2, 3, or something like. Really.
Okay. Or cumulative has a couple also, 6, 7, 8 are all
Oh, okay, yeah.
Bronze acidity. So I could do one of these.
Okay, sure, yeah.
Yeah, let's do. Maybe I'll do number 7. Let's see. Sorry, I'm just comparing them real quick. Okay, I'll do 7 and then I can do 8 if you want me to. Okay, so you're given A, B, C.
Kristen, which one is this?
This is number 7 from the cumulative alcohol problems. So we're going to compare acidity here. Okay, so we have to rank them in order of increasing Bronsted acidity and give a brief explanation. So I kind of talked yesterday about the different things that affect acidity, and one of them happens to be electronegativity, but then also size, right? So here we're mainly looking at electronegativity, because remember, electronegativity increases this way and this way across the periodic table. So fluorine happens to be the most electronegative, and that's followed by the bromine and the chlorine. So when we're looking at inductive effect, right, we kind of want to look at what is closest to our oxygen. So if we look next door for each of these, well, this carbon has a fluorine. This carbon has a bromine. And this carbon has a bromine. Oh, my cat is claiming her window. So that's going to kind of hint, well, like fluorine is definitely going to have the strongest inductive effect. So A is going to end up being our strongest acid. And then we're going to want to look to compare B and C. We want to look one more carbon over. So we're going to look at this carbon. So this one has a chlorine, and this one has a fluorine. So fluorine is definitely more electronegative than chlorine is. Oh, I was almost going to write F. So B is going to be our second strongest, and then C is our last. So this is increasing. Acidity. And resonance also plays a part. So, I mean, if we were to look at number 8, once again, we have, this is going to be A, OH, CF3. So this is A. B is going to be this. OH, CF3. OH, OME. This is C. Okay, so we're basing this off of resonance and inductive effect. Oh, okay. How do you do this to me? So right away, hopefully, you can see that we have a withdrawing group, we have a withdrawing group, but here we have a donating group. And that's because we have an electronegative directly on our pi structure, right? So there's all these pi bonds, right? With the benzene ring, it just goes around and around. This can contribute its electrons. So this is electron donating. So that is actually going to decrease the stability and decrease the acidity, right? Because more stable, it's going to be a stronger acid. So C is going to be our least. So now we just have to kind of compare A and B. And to do this, we have to look at resonance. So we're going to remove our hydrogen for each one. And see which one is more stable, basically. So if we put these electrons here, you know what, I'm gonna did this the other day too. I think it's better if I have it like that. So then these electrons have to move onto here. And then they can move into a bond here. And then these go onto here. There's a negative charge, negative charge. Okay, but then we also have to compare it to B. And B actually is going to have more resonance because it's further away. And you can see that the electrons actually go onto this carbon, right? So they kind of skip around this carbon. They kind of skip it. So we can actually see without even drawing the next resonance structure. I mean, unless you needed to, I guess, for the exam. But we can see that B would actually be more resonance stable because the electrons would be going directly onto that withdrawing group because it has the 3 fluorines.
Kristen, is there a trick so you won't have to draw the resonance structures to know where the electrons would go? Since it looks like there is a pattern, like it skips one and then it goes to the next one and skip, you know.
Yeah, I mean, so you can see. Yeah, so it would go over, it would go over, it would go over.
Huh.
So the electrons are not going to go directly onto this carbon because this would be like the double bond, right? So
Right.
then it's always like 1 over and then skip and then 1 over and then skip.
Hmm.
Yeah, so you wouldn't have to, unless you actually had to for the question, but it might just be selection and answer. So B is more resonance stabilized because it has the inductive effect plus resonance. So A is going to be in the middle. Are you here to knock my papers over again? Okay. Any last questions then about anything? You want to say hi? Are you here to say hi? Okay. Well, you get to meet my cat.
Oh.
She's gonna knock all my papers over. You're welcome. I'm gonna go ahead and stop